The purpose of this lab was to analyze the motion of a spring with a mass attached and to apply Newton's second law and the energy principle to predict this motion in a computational model. We will construct a computational model and compare this model's prediction data to our experimental model data. Results show that the computational model could predict motion in a similar way to the experimental data received from tracker, and that the energy principle is. The main principles at play are Newton's second law and the energy principle. Newton's second law is given by force, mass times acceleration. This can be manipulated so we can find a new velocity. This is given by the first equation above. The energy principle is given by the total energy in the system equal to kinetic energy plus gravitational plus spring potential energy. A concept of Hooke's law is also used. It shows the relationship between the forces applied to a spring and its elasticity. I analyzed a provided video in which an object was attached to the bottom of a spring. In tracker, the calibration stick was placed to represent the relaxed length of the spring, 0.7 meters. The origin was placed at the fixed attachment point. I then found the location of each point mass manually. Tracker then gave me the x and y position. I then put in a CSV file. This file will be called in our Python code. In the Python code, I had to update our initial conditions. This first line updates the mass of the ball, 0.402 kilograms. The initial position is taken from tracker and is given here, along with the initial velocity, which we set equal to 0, along with our start. The CSV file containing all the x and y position data from tracker is initialized in this line of code shown first. The time step and the gravitational constant g is also given. Then solve for the spring constant, change in length, and stretch length of the spring. The first cluster equations show how I solved for the spring constant, Ks, which came out to be 6.88 newtons. S, or the stretch, or the compression, is used to find the spring force and energy. This was found to be 0.572 meters. Once we have our S value, we can then calculate L initial, or the spring's relaxed length. I found this to be 0.128 meters. This portion of code uses the bits we just found. It calculates the spring length at each time interval. L hat tells us the spring's direction. Remember the energy principle? The system energies are kinetic, gravitational energy, and the spring potential energy. For our initial energies, we set them equal to the values that are used later on. As time goes on and the mass moves, these numbers will change, except for gravitational energy, which will just remain the same, mass times gravity. First is Hooke's law, and the F net is a spring force plus gravitational force. After we find F net, we use Newton's second law to find the new velocity, which then can give us the new ball position. Since our ball position is changing, we get a new stretch and compression. This portion of the code updates the spring, makes it moves, and updates the visual model. The energy of the system at each time interval, the kinetic, spring potential, and gravitational energy must be updated. These changes in energy will be plotted over time. We can run our computational model to see this. Now, let's run our model. The red ball is the data from tracker, while the blue ball is the computational model. As you can see, they match up fairly well to each other, despite some discrepancies. This is probably due to me not accurately marking the point masses in tracker, or the experimental model experiencing some errors in resistance or unaccounted for forces. The blue arrow was the spring force, and the black arrow was gravitational force. The blue line on this graph is the kinetic energy, while the red is the spring potential energy, and the green is the change in gravitational potential energy. So, is the energy principle satisfied? We expect the change in energy is equal to 0 joules because the mass spring at Earth is included in the system. No work is done on the system because the system is closed, and the work will equal energy. The combined change in kinetic energy, spring potential energy, and the gravitational energy equals 0. Therefore, work and thus a change in energy is equal to 0. If you look at our graph, energy, the yellow line, is equal to 0. Energy is conserved and the energy principle is satisfied. I found the oscillation period, or time between peaks, by looking at the graphs at the x position and the y position in tracker and averaging the times. I found the x oscillation time to be 1.697 seconds and for the y oscillation period to be 1.526 seconds. These values are close to each other, and this makes sense by looking at the equations. For the x, or the pendulum harmonic motion, we see that both have 2 pi. But x uses length and gravity, whereas y uses the spring constant. Thank you for watching my video.